Go ahead.
All right. So uh, the original goal of this project was to analyze the efficacy of various different machine learning models to predict financial derivatives prices. So the strategy that we set forth on was to test error for these different machine learning models. And that error is going to be predicted against randomly generated Black-Scholes data. So we employed about 11 different machine learning models. So anything from kind of extra trees regressors, lasso, MLP, which is a artificial neural network, and much more. Some of these models are going to be linear, and some of them are a little bit more advanced than that. So we'll get into the intricacies between what worked and why. So the data was generated with code, and this is following the Black-Scholes equation. So it's generated as the Black-Scholes equation and was kind of like randomly assigned. So we created over 10,000 instances of this data. So based on those parameters, we created Black-Scholes data, and we explored the data first off with the correlation matrix. So we're looking at how time, volatility, moneyness, and price compare to one another. So most notably with looking at all this data, price is heavily influenced by all the parameters, mostly time, or has the highest correlation with time for now. But all these parameters have pretty significant influence. Furthermore, if you look at the correlation between price, moneyness, time, and volatility, that would be the first row at the top. There isn't any obvious linear pattern, linear trend. So based on this, we expect the nonlinear models to perform the best. So that would be MLP, neural networks, decision tree, random forest, and a couple more. But yep, those are the main nonlinear performers. And so when we test the results for this, turns out pretty much how we expected. The linear models, including SVR, AVR, and LR, those far and wide had the largest test error, while the nonlinear models seem to perform very well. Almost no visible error on this chart. So kind of with that out of the way, we wanted to explore this a little bit deeper. So what happens if we separately analyze data by moneyness levels? So moneyness, just to recap, is strike price divided by stock price. And to start off, we created a heat map that demonstrates the standard model error, or standard error of the model predictions. And something interesting that we can see kind of right off the get-go is that some of the linear models perform better at lower moneyness. So for example, linear regression starts at kind of a paler red or paler color in the heat map, and then gets a little bit darker towards the right. So this is something maybe unexpected or unusual that we wanted to look into a little bit further. So kind of under the direction of Harium, we started analyzing each moneyness category separately. So starting with kind of an extreme example, a deep in the money option, moneyness less than 0.4, we did the same data exploration and found some interesting results. So price and moneyness have an almost one-to-one correlation, while price has very little to no correlation with time and a very weak correlation with volatility. Furthermore, if you look at the chart on the right, the price and moneyness chart is almost perfectly linear. So this kind of leads to the hypothesis, well, perhaps when you have in the money options, maybe linear models will work best. And that is exactly what we can see here. The linear models seem to outperform for in the money options. So as you can see, MLP, which performed very well last time, is actually doing relatively much poorer. And something like linear regression has almost no visible error. In contrast, looking at kind of deep out of the money options, we wanted to explore if there's any trends here. And it looks like time and volatility are much more dominant. And you can see that it kind of expectedly nonlinear models become much more suitable for price prediction. So linear regression support vector machine did pretty poorly. Kind of the trees, the random forest did much better by comparison. And then finally, looking at the money options, you would kind of expect that some of the linear models to perform poorly, and that's kind of what we're seeing here as well, especially with the support vector machine and the linear regression. Interestingly, though, the MLP, the neural network machine learning model, didn't do as well here. So to kind of wrap up the findings that we uncovered this semester, separately analyzing options at different levels of moneyness pretty dramatically influences the efficacy of different machine learning models. So when looking at all levels of moneyness as a whole, so deep in the money, deep out of the money options, and you're using the same model, nonlinear models are far and wide the top performers, and something like artificial neural networks seem to be really advantageous for this. But if you're separately analyzing deep in the money options, perhaps they can be better predicted by linear models, while out of the money options are similarly predicted by nonlinear models.